All right, talo falava, malolele, kia orana, and welcome everybody to another episode of our Voices for the Pacific. Today we're joined by Dr. David Vieque Galvez, who is going to be walking us through a very unique part of our discussion in our series, based on the scientific findings and the general consensus of the scientific community around climate change. Now, Dr. David Galvez is a biologist and ecologist for Colombia, where he studied the behavior of mixed species bird flocks in the cloud forests of the Andes. He completed his PhD at Massey University, where he studied the breeding ecology of the iconic kiwi. He is currently studying on how organisms adapt to changing environments and ecosystems in a climate change context. Dr. David Vieque Galvez will also be giving us just a presentation today, so no moderated discussion, and will have his own presentation for us. We invite you to post any Q&A in the Q&A section, and we will have the opportunity at the end to walk through each and every one of those questions. Dr. David Galvez is also joining us today from Colombia, so we wish him well and would like to pass him the time.
Kia ora, hey everyone, and thank you, Richard, for that introduction. Yeah, I'm very happy to be here from the other side of the Pacific, representing the wider Pacific region. And as Richard said, this talk will go through many of the scientific aspects of climate change, but always keep in mind that this will be a bird's eye view of what this phenomenon is, because it's a very, very complex phenomenon that takes into many fields. And I'm going to talk a little bit about some of those fields and how they have contributed to create the knowledge that we have today of climate change. But also that there are not only the aspects from the side of ecology, biology, paleontology, and climatology, but also there are social, economic, and political aspects of it, which I'm not going to delve much into, and I think there will be more discussion about in the near future. But let me begin with just some of the things that we all have heard in the media that have made us talk about climate change. Before that, I just want to give you an idea of what ecology is and how this perspective helps us to understand some of the aspects of climate change. Unfortunately, English doesn't have a differentiation between ecology as a science and ecology as a advocacy or ecology as kind of a protest in a sense. But they are strongly linked. So ecology as a science is a science that is all about the interactions between organisms and their environment, or organisms and each other, and how do they evolve, how do they, as I say, interact and change over time. It is also about the change in ecosystems, how the ecosystems themselves evolve as the planet changes. And that's something we're going to talk about quite a bit. The many changes that the planet has gone through throughout its history. So one of the things that I would like to start with is that we probably all have heard that scientists have warned us about the possible increase in 1 or 2 degrees over the 21st century. Some said that by the end of the 21st century, we will see an increase in 6 degrees Celsius in the atmospheric temperature of the Earth. And of course, for most people, that will sound like not that much. In a single day, we can go through a change of 10 degrees. A city like Wellington, for instance, can be easily 5 degrees one morning and rise to 15 in the afternoon. And actually, that's what I'm experiencing here in Colombia at the moment, is going from 13 to 25 in a single day. But to understand that, we need to go and talk about the difference between weather and climate. So the first thing is, what is weather? Weather is what we experience every day, those drastic changes. For instance, I think you probably are very familiar with this app. I quite like it, from MedService, that we all check every morning to know what to wear or if to bring an umbrella or not. So as you can see here, there are some variables such as temperature, humidity, rainfall, and these variables constitute weather, but are also what constitutes climate. So that's why it becomes a little bit confusing when we talk about those two. But weather specifically is what happens in short periods of time, one day, 1 week, and that do not have such an impact in living beings, because organisms need to be adapted to withstand these changes of 10 or more degrees, or an abundant rain one day and kind of a drought the next. For instance, I like the example of the Sahara Desert, that it can go from 50 degrees Celsius during the day, but fall to 0 degrees at night. But important there is that you can see that the Sahara Desert has a very low biodiversity, very few living beings that can actually accommodate that. But in many other parts of the world, what we see is that, imagine a plant, for instance, that can withstand an abundant rain one morning, and then the next day being quite dry. And at the end of the day, probably the plant will be a little bit wilted, but rain will come back soon. And that's what we know as a weather. On the other
Sorry,
hand,
I don't mean to butt in.
sorry,
Dr.
yeah,
Galvez,
okay.
are you able to turn on your slides for us, please?
Oh, I'm so sorry. I thought they were, I was going hard on it.
Just for context, you were already starting to blow my mind. So without any visual context, I was starting to kind of.
Sorry.
That's fine. Yeah.
Okay.
Great.
Yeah. Okay. Perfect. Yeah. So this is what I was showing you when talking about weather. And well, once again, to talk a little bit of the app of MedService, I really like how complete it is, showing you, for instance, the satellite kind of projection of how rain is going to be. In contrast to this, we have what climate is. This graph taken from a World of Weather, which is actually quite a good website for these things, shows you the average temperature and average rainfall in the city of Wellington over the past 12 to 13 years, because it starts in 2009. And I would like for you to see first here in the year 2022, just what has been of this year, and also around the year 2018, that the average maximum temperature for Wellington went over the 20 degrees. So that is telling us those years, that the whole year in general was quite warm, while we had other years here, like 2009 and 2010, that were noticeably colder. So some clarification on this graph: they take all of the coldest temperatures of each year and they create an average of that, all of the warmest temperatures of each year and create an average of that, and then you have the total average, which is in between. And this is important because if you just take an average, that won't be as informative, because it will seem that all the years are more or less the same, especially having those maximums and minimums. But what I want for you to remember of this is that climate is something that it takes a long time. Even this graph on itself is not something that we will consider climate in the terms that we use for climate change, because we talk in average of 30 years. So what have been the changes in those 30 years in temperature or in rainfall, for instance? And here we can see that the past couple of years in Wellington have been very rainy. And this has a lot of implications or ramifications for living beings, let's to say crops and livestock. Because if we go back to the example of that plant that can wilt at some point, but then the rain will come back. If the rain doesn't come back, that plant will die. And that's exactly what happens with crops and with livestock in those bad years. And again, that has an impact on the economy, the farmers, and the society as a whole. So the climate is something that affects us all very deeply. And I think, unfortunately, our societies have become more and more detached of those connections or of where our food comes from. And then it dilutes in the discussion. So that is the difference between these two concepts, weather and climate, and the importance of understanding climate as the big picture. But how big can that picture be? And that is when it becomes interesting from the point of view of paleontology and paleoecology and paleoclimatology, that the Earth is extremely old. It has approximately 4,500 million years, sorry, or 4.5 billion years. I would like for you to try to imagine that length of time. And it is amazing how we've been able to reconstruct most of the Earth's past. Earth has been divided in a series of eons. There are lengths of time. There is some periods, of course, that we don't know that much what happened because evidence becomes eroded in all of these kind of astronomic ballet of things that are constantly happening. So I'm going to talk a little bit of what is known as the Phanerozoic Eon, which is the eon that we are in. And it begins about 541 million years ago. And it is quite interesting how we have reconstructed the weather of these past eras. So what you're seeing here is a reconstruction of the temperature as of these different periods. And you can see that in the x-axis, you have quite a length of time. It's beginning from 542 million years ago. And this is not measuring you in the y-axis, the temperature directly, but the isotopes of oxygen, which has been used as the proxy for measuring temperature, as different organisms, rocks, and different materials fixate different isotopes of oxygen. And that can tell us, depending on temperature, or to say it better, those isotopes are fixated depending on temperature. So that's why it can be used as a proxy. So the more presence of oxygen 18 or 16, that will indicate us more or less what was the temperature at that time. And you can see that in the Phanerozoic Eon, there has been drastic changes in temperature. And here actually they have pointed out what have been glacial periods. And those are times where Earth has pretty much frozen, or big parts of the Earth have frozen over, and the overall temperature of the planet has dropped significantly. And in some of these periods, actually the atmospheric temperature has reached 40 degrees Celsius. So imagine that is pretty much the whole Earth in an eternal Australian summer. So that will have a lot of impact for many organisms and living beings. But fortunately, evolution is there, so they find their ways to adapt and cope with this, but it comes at an expense. So for once, you can see here these very, very drastic changes that happen on relatively short spans of time. And I really emphasize the relatively because this is a matter of millions of years. And it goes from one extreme to the other. So that will be basically climate change. So what we can say is that the Earth has gone through climate change many times in the past. But what happens when there is climate change on Earth? And this is what happens, is generally mass extinction. When we have a drastic event of climate change, a lot of the biodiversity of Earth disappears. And that's other thing that you probably have heard a lot, either in the media, or even if you are walking by Parliament and you see people with banners when they are protesting for climate change, that we are facing the sixth mass extinction. And that is actually quite interesting because indeed, Earth has seen at least 5 mass extinctions. But also, what does that mean? What is a mass extinction? Because extinction is something natural, actually. Pretty much all species become extinct at some point or another. And to be honest, what most scientists agree on is that 99% of all the living beings that have ever existed on Earth are now extinct. But then what does that mean in this context of mass extinction and extinction as a natural phenomenon? there is what we biologists call the background extinction or background extinction rate. And this is about, the rate at what you would expect different lineages, for which I mean different species or different taxa will become extinct. And this rate has been calculated to different types of organisms because it depends on many variables. But for instance, a number that I wanted to share with you is that they have calculated for mammals that we would expect one species of mammal to become extinct every 200 years or so. This is obviously kind of an estimate because, well, we cannot really predict what would happen or when a species will become extinct. They become extinct because their local environment changes. There are new predators. We saw that very much when Europeans arrived to New Zealand. The introduction of stoats and rats and many species of birds went extinct. So this is more or less what happens. It happens sometimes in bigger amounts. For instance, when South America and the Panama kind of connection start rising from the sea, that allowed the migration of a lot of fauna from North America to South America. And it happened more or less what happened in New Zealand with the introduction of mammals. All of these new species could predate on the species that existed in South America, and a lot of them went extinct at that point. But that took few thousands to 100,000 of years to happen. And that is the difference with mass extinction. Mass extinction is when a big proportion of the biodiversity, generally of Earth, goes extinct over a relatively short period of time. And I'm going to go with you through those 5 mass extinctions, also to see the different reasons that led to all of these climate changes. So let's begin here with the Ordovician Silurian extinction. This was caused by a glaciation. And at this time, most of the life was aquatic. So most of the living organisms were living in shallow seas, in tropical seas. And when the planet started cooling, it's not really well known why it started cooling, but there are different hypotheses. Some of them is that the rising of the Appalachian Mountains start trapping carbon very rapidly, which caused the opposite effect as what we're seeing with carbon dioxide being released into the atmosphere, creating that greenhouse effect. So what caused is that the Earth started cooling very rapidly. Water was trapped in glaciers or in the frozen continents. So the sea levels dropped down and the waters became cooler. This was a shock for all of these marine organisms, and approximately 85% of all species of Earth disappeared at that time, disappeared entirely from the fossil record, and it took several million years for the biodiversity to start recovering. Then, not too long after, we have the late Devonian mass extinction. At this time, some organisms were coming out from the sea and colonizing the land. We start seeing some plants and some amphibians, insects. And this is quite not well understood mass extinction. We only know that oxygen plummeted rapidly. Land plants could have contributed to that because, they for once trap carbon dioxide and release oxygen, but they also use oxygen for respiration. Algae also became quite abundant at this period, which made the waters quite toxic as algae died also from the drop in oxygen. And that again started killing a huge amount of species. Actually, it is about 75% of the species that existed at the time. I put here the image of a supernova because some of the other hypotheses suggest that extraterrestrial event, supernova exploding, sends some radiation, and so it can happen with the sun, for instance, that affected the weather of the planet. And this extinction took about 20 million years to happen. So this is what I'm talking about with a relatively short length of time for mass extinction. This was 20 million years. So still for human terms, especially when we see what is discussed about climate change, that begins at the Industrial Revolution, so it's 170 years ago, it seems quite a disproportionate comparison of time. Then this is one of the mass extinctions that I found the most interesting is during the late Permian. This one is much better understood, and it has been one of the most catastrophic that the Earth has seen. This period here is usually known as the Great Dying, as 95% of all of marine species died, and approximately 75% of land species died. And this is a little bit well known what happened then, and it was the explosion of many massive volcanoes in what is now Siberia that released a massive amount of carbon dioxide and other gases that created that famous greenhouse effect that started warming up the planet, but also that led to the leaching of a lot of toxic substances in the water, making the water poisonous, and that's why most organisms could not cope. And this one is also quite a good example of a mass extinction in the sense that it happened very quickly. It took 60,000 years for all of this great dying to happen. So once again, we're seeing 60,000 years. When we compare to human history, well, we're saying 500 years ago was the Renaissance. 1,000 years ago, Maori were coming into New Zealand. Europe was in the Middle Ages. So when we take it to 60,000 years, still quite a long time for the human time understanding. Then we had the Triassic mass extinction. Again, this one is a little bit more mysterious, but at this time, all continents were joined together in what was known as Pangaea. And because that supercontinent was so big, most of it was a desert because it was difficulty from rain actually coming to the middle of the continent. But also there was some what was known as the Central Atlantic Magmatic Province. So once again, a region with a lot of volcanic activity that released a lot of gases, a lot of lava, and that again affected the weather of the planet by generating those kind of greenhouse effects. And this one was not as catastrophic as the Permian, but a very big proportion of the living beings died. Then that led us to the most well-known mass extinction event, which is the KT, the Cretacic Quaternary Boundary. And as you probably have heard, this happened by the collision of a huge asteroid that collided in what is now known as the Yucatan Peninsula, or in that area of the Caribbean. And this is quite interesting because it's good to put in perspective what a single event can cause, but how still it remains somewhat local, because the asteroid impact in that region, and of course, what follows from that is wildfires, a lot of debris being launched into the atmosphere, darkening the planet, and many plants start dying because they cannot photosynthesize, and tsunamis also circling the planet. But it still remains somewhat local. Just the effect of it, those clouds, those tsunamis start killing more of the biodiversity around the globe. So that still will take a few thousand years to create that huge extinction. So creatures like dinosaurs went extinct because when plants could not photosynthesize, then food became quite scarce, and then the big herbivores will die, then the big carnivores will die. But it gives the opportunity for smaller creatures, for instance, birds and mammals, that could thermoregulate, which means that they could maintain a body temperature. So if the temperature would become too hot or too cold, they could moderate that a little bit better. And by being small, they could just find sustenance with whatever little things they were. So that's what allowed for life to recover. And that's what has happened at every point. Fortunately, never has been a mass extinction where 100% of the biodiversity disappears, because I don't think we know what would happen then if life would ever recover. But whatever is left is the material for the new species to evolve and ecosystems to recover. And I want to then introduce a little bit of some ideas from biology and evolution here to help understanding how this process happened. When you hear the word evolution, probably one of the first famous sentences that comes to mind is the survival of the fittest. This is an expression that most biologists are trying to get away from, because it doesn't quite convey what actually happens. So a better understanding of it is the survival of the form that will leave the most copies of itself in successive generations. So basically, by surviving long enough to reproduce, then your offspring has the possibility to migrate to new places, to establish, to exploit new niches, and then become an established population and explode, diversify as well. So I have here a little bit of an example of how some of these processes happen. So imagine that you have one island with some birds, and this happens quite often that some of the birds either migrate, get pushed by storms, and find themselves in new places. These new places can present a lot of opportunities, but also a lot of challenges. But if those few birds that are in this new place are able to reproduce and cope with whatever is there, there is the possibility to establish a population just the same as the one that they left. But most likely, each environment is going to be different. So, for instance, if there are predators that they weren't in the previous place, only those that have certain characteristics, let's say that as opposed as what you're seeing here, some brightly colored birds, they're a little bit duller, they will be more likely to survive those predators because they won't be as visible. And those with those characteristics will have more chances to leave more copies, but only those copies that have those characteristics of being more and more duller are the ones that are going to survive. So after long enough, you will have an entire population that it has diversified from that original population, but has completely new characteristics that has allowed them to exploit that new environment that they are in. And even from that, if there are not niches that are being utilized, that allows these same species to start exploiting those niches. And also by that process of natural selection, by random mutations that allow them to explore these spaces, they are going to be kind of perfecting themselves to exploit these spaces. So they might develop bigger, stronger beaks to use a different food source and become bigger to, for instance, overcome land predators. And to reinforce the idea of that background extinction, for instance, when in the previous population, the conditions become harsh and food becomes difficult to come by, that population can just become extinct. And that is something that constantly happens all the time and is what we can consider natural. What we're seeing today, for instance, with the anthropic climate change is precisely that we're moving the living beings of the planet. We're seeing a lot of birds migrating and staying in their places that they are migrating because they are finding better conditions there, as opposed to the changing conditions from the environments that they came from. Something that is quite observable these days, there's a lot of rich research in these topics, is in mountains, where because the atmospheric temperature is rising, plants are migrating up. And well, by migrating, their seeds manage to get up, and only those that are higher up in mountains are the ones that are able to become established. And as temperatures continue to rise and mountain caps become warmer and warmer, then plants and animals follow that trend, and you will be finding them higher and higher up in the mountains. So life has always a way to recover and to adapt and to migrate and find new places, new niches, and new ecosystems. And this is an important aspect of what is happening now with climate change, that ecosystems are shifting. Deserts are becoming bigger, for instance, or some tropical forests are changing in their morphology of plants and not being tropical anymore. So the planet is just following its course, but it is the sudden change that we have introduced that is making these things happen much faster than has ever happened. But at this point, you're probably wondering, how do we know all of this? Because I'm talking about a million years ago, but how do we know that any of this is true? And there are many fields that have been studying these phenomena separately. And what is very interesting is that all of them are finding more or less the same things. So for instance, what I've been talking about, diversification, evolution, and all of that, we have the fossil record. So as I mentioned before, in one of these mass extinctions, how we know that there is a mass extinction is that we go and dig deep into the ground and we start finding some types of fossils. These will indicate what type of environment that was. For instance, if you find ammonites, such as those in the slide, that will suggest that that was a marine environment, which today might be something completely different. So for once, that already suggests that something has changed from then to now. A good example of that happens here in Colombia. Is one of my favorite places. It's called Villa de Leyva, which is a colonial town high in the Andes. It's about 2,000 meters above the sea level. And it is one of the main paleontological sites of Colombia because they have discovered an amazing amount of fossils, but all of them are marine fossils. We have marine dinosaurs, we have ammonites, we have crustaceans. So how can those fossils be in such a high mountain? And it's because of that. The Andes has rose from the sea, and what used to be a sea now is a high mountain that has the ecosystem of a cloud forest. So in that sense, we know how these ecosystems have changed. And in the fossil record, we can see how the biodiversity has changed. And in these cases of mass extinction, when we go there and dig deep, we find a lot of fossils, and then all of a sudden there is none. And all of these lineages disappear. Only few of them remain. And that's how we know something happened there that changed drastically and quickly that killed all of these organisms that all of a sudden are no longer there. On the other hand, we know the relationships between species. Paleontology has given us a compared anatomy, so we can compare bone by bone and know how organisms have evolved from one another, because all living beings in Earth come from a single ancestor. We like to call it Luca, which is the last unknown common ancestor, who will be someone just at the tip of this round tree. And here you can see how from archaean bacteria, we are all related to plants, fungi, and animals. And how we start diversifying. This has been made much clearer nowadays with the advent of genetics and genomics and proteomics and many other sciences that look down to the genes, to the proteins, and can establish those relationships, and has helped to clarify very much what all of these relationships between organisms are. So by knowing these relationships, we can know how these lineages are related together, and that's how we can eventually calculate things such as that background rate extinction, because then we can see all mammals and how they have become extinct over time. Then we have from geology, the science of stratigraphy, which I invite you every time that you are in a road trip to look a little bit when there is exposed earth, because this is something quite beautiful to see how Earth just changes in different colors, and you have these stripes of different textures and colors. And that happens because in these different events, for instance, a river passes by, deposits sediment, that will have some physical and chemical characteristics. Then it becomes quite arid and you have sandstorms, then sand accumulates. So that's why you start piling up in that kind of linear pattern that indicates many of the things that have happened in the past. For instance, one of the events that are quite compelling about the KT event, that asteroid that came at the Cretaceous Quaternary boundary, is that in that layer, we find an element called iridium. This element is extremely rare in Earth, and we don't find it pretty much anywhere else. But in that time period, because this element is actually quite common in outer space, it's common in asteroids and in meteorites. So after that impact, that it pretty much put a layer of iridium pretty much all around the planet, and it is consistent. So when we dig down to what would be the Cretaceous strata, we will find iridium. So that's how we start piecing up together that story that is the story of Earth. In a similar way, we have the ice cores that have become quite popular in climate studies these days, because it's pretty much the same process in the ice cores of Antarctica or in the Arctic. In different seasons will allow for different gases to become trapped in the ice core, such as carbon dioxide, such as oxygen. Also, events like dust storms or other type of climatic phenomenon will be registered there. But also they have something quite interesting that I talked in a previous slide, and is the isotope composition, because again, because of temperature, different isotopes of different elements will be present in those ice cores. So it can be oxygen, it can be carbon, etc. And again, it has that kind of layer pattern that allow us to look back into time. Also, there is the field of dendrochronology. This one is quite well known, is the three rings. And basically, this works in a way that a tree will grow best when conditions are nice and warm and they have enough water. So you will see thicker rings. In years that they have experienced drought, that they have experienced colder climates, then the rings will be thinner. And actually, I found this image quite amazing, because this is a tree slice from the 1690s that goes from the 1690s to the 1740s. So it's quite a decent lifespan for that tree. And then you can see basically year by year, this was extracted in Germany, so a country that around this time period had the seasons as we know them. So we can see at every summer how much that tree has grown, and as a proxy, how has the weather been. And this is quite an interesting time for be looking at these things, because we're just at the beginning of what was the French Revolution, that many historians now believe it was quite affected by a little ice age. So at this time, the weather of Europe became quite cold, crops didn't yield, and you probably have heard the story of people not having bread because the crops failed. And then Marie Antoinette saying, well, let them eat cake. That is actually not accurate. That was just a rumor spread at the time. But it is true that at that time, the population of Europe was experiencing a lot of difficulties with their crops because the global temperatures dropped down. And that is registered on these trees. Then, just to explain a little bit more about those isotopes, basically all elements have something that is known as half-life. So an atom will start losing neutrons over time, and that is what will create different versions of that isotope. And that half-life changes drastically between elements. You probably have heard about a carbon-14 for dating many things, for instance, mummies in Egypt, and all of those sort of things. So carbon-14 is something that you're going to find in organic matter, like animal tissue, plant tissue, and it has a half-life of just a few thousand years. So it's perfect for dating things like mummies, things that were created 4,000 years ago. Then you have other elements such as argon, or here that we have hafnium tungsten, and this will take from, for instance, 500,000 years or 9 million years to decay, to go from one isotope to the next. Which means, for instance, for carbon, you go from a carbon 16 to carbon 14, 14 to 13, and in that losing of the neutrons, we can calculate time because it's very stable. And isotopes are also very interesting because living beings seem to have a taste for some isotopes. For instance, in the field that I have worked the most with a mineral called hydroxyapatite, which constitutes eggshells and tooth enamel. And you can see the different ratio of oxygen isotopes and carbon isotopes. And what happens there is that plants tend to fixate different isotopes depending on their metabolism. So plants from arid regions will fixate or use more of one isotope of carbon, while plants that have metabolism for tropical environments will fixate another. And these, when they are eaten by birds or by mammals, will become fixated in their tooth or in their eggshells. So when we look back at that, we can create a landscape of what the weather was at that particular moment when those animals died or when those eggs were laid. In a similar way, what we have here is the foraminifera and the coccolithophores, which are a kind of microscopic marine organisms, but that create shells of calcium carbonate. And once again, they do have a tendency for fixate particular isotopes of carbon in their shells, but also through the knowledge of phylogenetics, when we relate all of the living organisms, we can tell which ones are related to which and which ones are likely to appear in warm tropical environments or in cold Arctic seas or in drier environments. So when we look back on the fossil record and we find all of these little shells, we can tell this place was probably a warm tropical sea or it was cold and Arctic. So by putting all of these different pieces together from so many fields, we can reconstruct that history of the weather in the planet, the climate. And it is quite interesting that all of these sciences are finding pretty much the same. That's why I strongly believe that the narrative of the climate change is quite accurate, because in so many different parts of the planet, through so many different disciplines, we have been finding the same results over and over again. So now let's talk a little bit of, very roughly, how the climate works in the planet. The planet has a lot of cycles of energy and gases and matter that is what creates the phenomenon that we know as climate. So to begin with, many scientists have divided the Earth in a series of spheres of what they contain and how they relate their cycles to each other. So to begin with, we have the nucleus of the Earth, that is a magmatic nucleus, has a lot of metals. It contributes to the Earth as it radiates heat, because that is under a lot of pressure, which creates heat, and it radiates heat to make the Earth be a little bit warm. Then we have the lithosphere, which is all of the rock that surrounds the Earth, the mantle. This has many other subdivisions that can be very precise, but this is quite general. Over that, we have the hydrosphere, that is all of the water, all of the oceans, rivers, seas, lakes. Then we have the biosphere, which is all of the living beings. And this is quite important because things think that plants release oxygen, absorb carbon dioxide, but they also release carbon dioxide. All breathing animals release things like carbon dioxide. They use oxygen, they release methane, and many other gases that, as a whole, they do affect the climate of the planet. Then we have the cryosphere, which is where all of the ice caps are. So we have some frozen seas in the Arctic, a frozen continent in Antarctica, but all of the high mountains with perpetual snow, the permafrost of Siberia, and all of that constitutes the cryosphere. And finally, we have the atmosphere that is composed of a variety of gases, but mostly nitrogen and oxygen and other trace gases. Carbon dioxide is actually important there. So all of these different spheres contribute some gases, some energy, some heat, or some cold, and is what helps regulate the climate of the planet. I want to emphasize when I say regulate is just to maintain conditions for a given amount of time, because the climate of the planet is inherently always changing. So for instance, one of these cycles, one of the most simple one, is the water cycle. So as the heat from the sun hits the sea, the rivers and lakes, water evaporates, forms cloud. These clouds move around, but at some point there's just a drop in the form of rain, usually when they hit mountains or other landscape phenomena such as, and it returns, can be absorbed by the ground and become aquifers and become subterraneous rivers, or just fall directly into rivers, as we've seen, and go back into the ocean, or simply rain back into the ocean. So it's a cycle where the water is always coming up and back down. Another interesting cycle is the carbon cycle. So there is a natural carbon cycle where, for instance, things like volcanism, as we saw in the many mass extinctions, volcanoes release massive amounts of carbon dioxide that goes into the atmosphere. Then you also have the carbon dioxide released by many living organisms, and this joins the clouds formed by water. And there is an interesting chemical reaction that happens there, because when carbon dioxide comes in contact with water, and especially in the form of gas, forms a carboxylic acid. And this will rain in the form of acid rain. Funny enough, as terrifying as acid rain sounds, is part of the natural cycle of carbon. So this acidic rain falls into the ground, but here is the key aspect of what happens and how the earth regulates that carbon dioxide. This withers different types of rock, especially silica, and forms minerals. So the carbon becomes trapped there, and it doesn't necessarily come immediately into the atmosphere. So that's how the earth, in those events of enormous release of carbon dioxide, for instance, in the Permian, has been able to regulate back and trap that carbon in the form of carbon-based rocks. Also, if it is not too much carbon in the atmosphere and this rain is not too acidic, this can also go into the water, and that dissolved carbon is what many marine organisms use to build their shells, such as mussels and snails and all of that. So that also becomes somewhat trapped there. So the earth has some natural traps for carbon. So if this is happening naturally, how comes earth cannot cope with the carbon we are producing in fueling our cars or to power our industries? The problem is that we produce way too much, and actually it is almost at the level of the Permian, because we can see here the atmospheric carbon dioxide, how it was measured through different proxies. For instance, the Vostok ice cores, as I mentioned before, some low dome ice cores that they measure the amount of carbon dioxide in those cores, and those go back to 400,000 years. And you can see that the levels change. This is probably through that carbon process, the carbon cycle, and never going above 300 parts per million. But once we measure the current level, we're reaching the 400 parts per million. And this is making Earth, making very difficult for Earth to fixate that carbon again by withering the rock. Also, because accompanied with this development has been the extreme desertification and the chopping of many big forests. For instance, you can see what is happening right now in the Amazon rainforest. that is being very heavily harvested for ones to make room for crops and livestock, but also to extract precious woods. So as we reduce the plant matter that could also kind of trap some of that carbon dioxide, there is just not time for Earth to recover and trap that carbon dioxide, and now is becoming quite a big problem. And from that comes the known greenhouse effect, although nowadays many scientists prefer to call it the blanket effect, as it sounds a little bit more accurate. And basically what happens there is that by having a thick cover of carbon dioxide, some of the solar radiation can come through, but it becomes trapped, which overall starts warming up the planet. Once again, that's what we saw in the Permian. So the temperature of the planet is rising very quickly. And if we look back to what happens to many living beings when temperatures are rising, they cannot cope. It can be too fast, and then we start having a mass extinction. And this is particularly detrimental to our crops and our livestock because our plants cannot cope with these temperatures. And also think what happens with many plants that grow in countries that have seasons, for instance, things like apples, that they need a period of cooling over winter. When the seeds fell into the ground, they need to cool for some time, then to sprout in spring. But if there is no winter, then the plant won't have that opportunity, and probably if it sprouts, it will be weak, and if it continues to be hot, it won't be able to grow as a tree and produce enough fruit for our industries to carry on. So this has a very negative, very detrimental effect, not only in biodiversity and the ecosystems as a whole, which, as I said before, they will recover if they are just left alone, but in our economies and our societies. And definitely our societies won't have that adaptive capability to cope as quickly. Some of the other cycles that are being affected by this change in temperatures is known as the albedo cycle. So what happens is that when the sun sends its warm rays and it hits some surfaces that are clear or white, then the energy is repelled back into space. But when it hits dark surfaces, such as a forest or the sea, that energy becomes trapped and hitting that surface. You probably have experienced that phenomenon when you're wearing a black shirt in a very sunny day, that it becomes unbearably hot, because that's an interesting property of matter, that dark surfaces tend to trap that heat. So what happens here is that as the seas that are dark become warmer and warmer, then they start melting the ice, which reduces the white surface of the planet, which in turn allows the sea, which is a wider surface now, to become hotter and hotter, reducing further the ice. So this is what is happening with the melting of the ice caps, that again has quite been in the news. And that leads to sea levels rising, but also very importantly, changing the chemistry of our oceans. And we know, as we have seen this drastic rise in temperatures and concentrations of gases from the past 170 years, that it is strongly associated with the use of fossil fuels. Not only fossil fuels release carbon dioxide as a byproduct of their combustion, but there are also many other substances that are quite not dangerous, such as nitrogen-based gases. Also, they can produce some low-level oxygen that is extremely carcinogenic and toxic. But focusing on the carbon dioxide, is that we're seeing a very dramatic process in the change of the weather of the climate of the planet. And it is not only, unfortunately, the use of these fossil fuels is not only when we use them for cars, because of course it will be amazing if everyone could just change to electric cars or something like that. But the whole process of using fossil fuels is quite detrimental to the planet, because there is the extraction, the refinement, and the shipment of those fossil fuels that uses fossil fuels generally, then it produces all of this carbon dioxide. And this is a number extracted from the Forbes magazine in 2019 that pointed out that still fossil fuels constituted 84% of the world's energy consumption. So think that in many countries, and we're seeing that quite interesting what is happening in Europe at the moment, that we're saying that a big part of the EU is still quite dependent on fossil fuels and gas and coal. So that means that every time that someone turns on a light at night or cooks anything is just being part of this cycle. And this is pretty much everywhere. It's not only in the individual spaces at home where this pollution happens, is to that extraction, to that shipment. And also in industries, many of the things that we consume, the industries use fossil fuels to produce energy so they can produce whatever they produce. That is a current crisis in Spain that many industries have to stop due to the circumstances in Europe that they cannot produce anymore because they cannot have access to energy. And then we need to think, especially in countries like New Zealand, where many food products are imported, that those products come in ships that are using fossil fuels to move them around the planet. So it is pretty much everywhere. So at this point, it does become quite difficult to deny the fact that all of these human cycles are affecting the natural cycles, therefore affecting the climate of the planet. And not only that, I wanted to bring this here because this is something that has bothered me for quite some time, especially since the Deep Horizon spill in the Gulf of Mexico, that you can see here that since the 1970s, there has been oil spills pretty much every year. So we're not only changing the chemistry of our oceans because of the carbon dioxide that is in the atmosphere, which also dissolves, as I said before, in the cloud, but it also dissolves in the ocean, acidifying the ocean, stopping a lot of those marine organisms to fixate carbon in their shells, because keep in mind that a carboxylic acid is an acid, and those shells act as a weak alkali, so they react and they dissolve. So we're not only doing that, but we're constantly dumping tons and tons of oil into the ocean, not to mention plastic, which is derived from petroleum byproducts. And this is the breakdown of the global energy consumption by the Forbes magazine on 2018, I believe. And you can see the big proportion that constitute the fossil fuels, how nuclear energy, which I mean is still a controversial option, is only the 4%, hydroelectric only 6%, and renewables only 5%. It is also quite unfortunate that this big consumption of oil happens in the non-first world countries. Think the European Union, the US, they are big users of these sources, but they are also one of the biggest consumers of the planet of the resources that are produced anywhere else. For instance, here in Colombia, it's quite interesting that the 70% of our energy is hydroelectric. I know in New Zealand, a big proportion of the energy comes from wind or geothermal, but we're not the biggest consumers of it all. So think of all of the shipment of produce, of manufactured products. The manufacture that happens in these places is still based on oil and coal and natural gas. I take this opportunity just to introduce a concept that I find quite interesting, has been discussed in the literature quite a bit, and is what is known as the global hectares, the per capita global hectares. So it's basically an estimate of how much a single person needs in a space of land for sustenance. So that gives us an idea of sustainability. So how much is actually sustainable consumption? And they have estimated that to be sustainable and to fulfill the needs of a single person, 1.8 hectares are to be used. And it's interesting when you look at how much is actually being consumed in different places. The only places that are abiding by that 1.8 hectares per person are places like Guatemala or Costa Rica. But when you go to the United States, you have 8 times that amount. In the European Union, is 4 times that amount. So that's a thing that makes you think, how much are we actually consuming? I believe Australia and New Zealand are consuming 6 times that amount. So there are many components to this phenomenon that is climate change, that is not only if we're just using a fossil fuel directly, is in many of these transactions that we are producing more of these gases, changing environment, because for all of that we consume, it needs to be planted somewhere, the resources need to be extracted from somewhere, and that creates more of that. And this is one of the most terrifying things that could happen in the near future, and is that modifying the temperature and the chemistry of oceans, thermohaline circulations can be halted. This is a system of currents that depend on the density, the salinity, and the temperature of the sea that transport nutrients in the ocean, but also water of particular temperatures. So for instance, the reason that the Mediterranean region, Southern Europe, and to some extent the United Kingdom can enjoy somewhat milder conditions that, let's say, Scandinavia, is because warm water from the Caribbean and the tropical Atlantic goes up to that part of the world, warming up their seas and bringing a lot of nutrients that feed their fish and all of the other products that they can extract from the sea. By changing the chemistry of the ocean, this can stop, which means that the climate, sorry, I keep saying, the climate in Europe will change drastically. And what we can be seeing in the near future is the Mediterranean region experiencing much colder winters, which definitely will affect many of their crops and their exports, therefore their economies. Interestingly, the Atlantic current will also affect the climate in Canada, which is used to somewhat dry, long winters, but these winters are going to start becoming quite short and much wetter and warmer. Canada, for instance, is the main exporter in the world of pulses and some other grains. And if these crops do not have the right conditions, well, entire crops are going to be lost. And that will be a huge impact to the Canadian economy, but also all of the countries that are dependent on those exports to feed their populations. So this is when it started becoming quite a complex social phenomena, because when you start having depletion in food resources in some places, economic crisis and recession in others, that often leads to crime, to people revolting, to social instability, to political instability, and it can be quite a grim scenario for the rest of this century. So I want to leave you, I think I probably have gone over time, but I want to leave you with some messages from ecology. For once, is that ecosystems are in a constant state of flux and change, and this is inevitable. That's what we have seen throughout all of these eons of time that the Earth has gone through. So that led us to thinking there is not such a climax ecosystem or perfect balance for an indefinite amount of time. That's why climate change cannot be stopped, because even if we stop the anthropic climate change, the climate of the planet will still continues to change. And I think it's very dangerous for humans to try to intervene directly, because ecology is actually a relatively young science. It began in the 1960s and 70s. And what we are finding now is that ecosystems are extremely complex networks of interacting species, the biotic factor, and their physical environment, which we call abiotic. And it is through evolutionary mechanism that species fill different niches, but we cannot pretend to put species in particular places and expect them to do exactly what we want, because these interactions are extremely complex. So every time we modify something, the consequences are pretty much unknown. But what I want to say about the climax ecosystems is that we cannot expect to keep Earth being what it is now. It will change. What really needs to change for us to survive and to thrive is us, is our systems. We are the ones who need to adapt. We won't be able to change the planet ultimately. And I quite like this quote from Fritjof Capra, which is an Austrian ecologist who has been advocating for the coming back to a more holistic view of nature and understanding nature and social systems. And something that is very important, I guess the biggest message from ecology is that diversity is the key to survival. A diverse ecosystem that has many, many species has the possibility of those species filling niches and being a little bit more stable. That for a benefit. So going back to the idea of the mass extinction, the more species we lose, the more unstable the whole planet will become, and things will go very bad very quickly. The more species we have, that buys us at least some time so we can start understanding better all of these processes and adapting our societies and ourselves to the planet. Then we have on the consequences to kind of close out this talk. As I said, ecosystems are very rapidly changing, and that's why we're facing a mass extinction, because this is happening at a speed that Earth has not seen at any point. We are not having the 60,000 years that they were in the Permian. This is happening in 170 years. And by the end of the century, things are getting even worse. And those ecosystems that we humans are dependent on will be completely disrupted, and we don't fully understand how much we depend on every little creature, on all of those pollinators, and all of these insects in the earth that aerate the air so nutrients can get there and crops can survive. Changes in oceanic currents will produce drastic changes in weather patterns, that I do mean weather and day to day, and also in the climate. So that will endanger many crops and livestock. And all of these will lead to further the increasing inequality that exists in the world, that also taps into that greater conflict, mass migration that we have seen that just in these couple of decades of the 21st century, and that creates all sorts of conflict. And as I said, is that we cannot keep up with these changes, and it is the moment to learn from an evolution to adapt, and that is basically by changing our energy sources, but especially by changing our consumption patterns, because the world we live in is a world of extract, consume, and discard. Earth cannot cope up with all of that residue of our activities, nor can renew the resources at the rate that we are consuming. So my general invitation to you at every point is like, think twice before buying anything. Just really consider if you need it, if it is worthwhile, or you are just trying to fill a void within yourself just by purchasing something. And definitely our economic and political systems need to change. That is definitely what needs to evolve and to adapt. Otherwise, we are pretty much screwed. So you could also think, if nature and the climate are in constant change, why should we care if the climate is changing now? Of course, we could not care. We could trash the planet, but that is only at our own expense, because we're just only making uninhabitable to us. And I want to give you an example of that, and that is the exclusion zone of Chernobyl. No human can be there, that's for sure. But since 1986, when that happened, what they are finding is that wildlife has returned. There are wolves, there are moose, there are raccoons, and all sorts of animals and plants are coming back to Chernobyl. So life can adapt eventually. And as we have seen with the mass extinctions, life will go on, the planet will go on. We are the ones that are at a loss here. And yeah, we probably cannot evolve biologically as fast, and even less our societies. Also that we are very complex creatures, and right now it seems a race for who becomes the next billionaire, and it's all about me. But we often forget that we are that we as humans have achieved whatever we have achieved because we have worked together to build the societies that we live in, and we need each other. So just caring about yourself is something that also won't hold in the long run. And just don't forget that we need nature, but nature does not need us. So we're the ones that can lose here. And just another quote from Fritjof Capra. Shallow ecology is anthropocentric or human-centric, and that's basically a mistake, because it views humans as above or outside nature, as the source of all value, and ascribes only instrumental or use value to nature. Deep ecology does not separate humans or anything else from the natural environment. It does see the world not as a collection of isolated objects, but as a network of phenomena that are fundamentally interconnected and interdependent. Deep ecology recognizes the intrinsic value of all human beings and views humans as just one particular strand in the web of life. If we are capable of going back to the environment to reconcile ourselves with nature, creating social nature systems, then humanity has a chance. And now, to finish, I promise, this is a quote that I quite like from Jean Baudrillard, to think a little bit of what modernity is. And throughout its history, it was capital that first fed on the destruction of every referential, every distinction between true and false, in order to establish an absolute law of equivalence and exchange. Just some food for thought, and I'm happy to hear some questions.
Awesome. So thank you for that presentation, Dr. Galvez, and we appreciate the information that you've given us. One of the central questions that was may link all the way back to your initial presentation, and I think this is one of the more generic ones, is if we see climate change as such a long-term destination, like we're looking at decades and decades, how accurate can we assume those assumptions will be in playing out? So, when we talk about the 1 to 2 degrees or climate change in general, and then we play it in the terms of planet Earth, not human cycles, which is decades and centuries, how accurate do we depict those to be?
Well, that is actually a good question. I don't think that it will take that long for us to see the effects of climate change. As I was talking about the thermohaline currents, there is evidence that they are stopping now. So that is not going to be in 20, 30 years. Might be much sooner than we expect. The other thing is that those predictions, think a little bit what has happened with COVID. We are also trying to do things to change. There is the COP26, there are these agreements signed between countries to stop carbon dioxide and all of that. So all of that is going to affect to some degree what can happen. It will be different if we were doing nothing. But the evidence is quite strong, and it seems that For instance, even a 6-degree increase by the end of the century is quite likely. Sorry, I think you have your microphone muted.
Thank you for that. Thank you for reminding me. I am aware that we are running a little bit over time, and we do understand that some people may have finished their lunches and may need to get back to work. But if anybody has questions, feel free to reach out to the National Library, and we're happy to exchange any information and relay any questions back to Dr. David Vieco Galvez. But other than that, we'd like to thank you for your time, for joining us, to the audience, and also a huge thank you to our guests today. We are definitely a lot more informed and enlightened about the history and scientific findings, and we thank you once again for being part of this program.
Thank you so much for having me. I really enjoyed this opportunity to share something that I'm quite passionate about.
Great, thank you. Well, everybody have a good rest of the day, and same to you in Colombia. And we will see you next time for the last section based on legislation and policy. Thank you.
Looking forward to it.